In this video, we're going to start section 1.4, which is on continuity and one-sided limits. So let's begin with a warm-up. Look at the piecewise function graph below. Identify the values for C where the limit does not exist. Now this should be fairly comfortable for us at this point. How many different values can you find for X where the limit does not exist? There are two different values. The limit does not exist at X equals -2 because of the asymptote and one side goes up and the other side goes down, and also at X equals 0 because one side is going to Y equals 1 and the other side is going to Y equals 2. Those are the only two places where the limit does not exist. Keep in mind that here at the whole, at X equals 2, we can find the limit. What is the limit as X approaches 2? Well, the Y value that we're approaching from both sides is 0. Please note that f of 2 is actually -3, so they're not the same value. So one of the main topics for today is continuity. So I ask you to think, if I tell you that a function is continuous, what does that usually mean about the graph? The first thing that people usually tell me is that you can graph it without picking up the pencil. A good example of this would be a polynomial, like a parabola or a cubic function. I can draw the entire thing without ever picking up my pencil. What else do you think of when you hear the word continuity? I think, well, the line or the graph keeps going. It never ends. Another thing is to consider what the domain would be. Think about a polynomial again. What's the domain of a polynomial? That domain is all real numbers. So for a function to be continuous, that means the domain has no breaks in it. So these are just a few things that you might think of when you think of continuity. Let's take a look at the formal definition of continuity. The definition states that a function whose graph is unbroken, meaning it has no holes or jumps, or is otherwise uninterrupted, it's called a continuous function. There are three conditions that have to be met in order for a function to be continuous. The first one is that f of c is defined for every c value, or every x value. So you can find a y value to go with every x. The second condition is that the limit as x approaches c of f of x has to exist. So you have to be able to find the limit everywhere. And last but not least, the limit value has to be equal to the functional value, f of c. These three conditions are incredibly important for you to know, so make sure you understand them. There's different types of continuity. A function could be continuous everywhere, meaning over its entire domain, or it could be continuous on just an open interval, say, from A to B. So we're going to look back at the graph that we had in the warm-up. You'll see it below. We want to name the open intervals where the function is continuous. So let's see if we can figure out what those are. An interval where the function is continuous, the first one I see, if I start all the way on the left-hand side and start tracing the graph, I can basically draw this without picking up my pencil. That section of the graph is continuous. The domain of that section is -∞ to negative 2. So this function is continuous from negative infinity to negative 2. Notice it's an open interval. There is not a bracket with the negative 2. That's because negative 2 is an asymptote. I'll never actually get to x being negative 2. How many other open intervals are there? There's another one, starting with this part of the graph and ending with this point. That interval starts at negative 2, but again, does not include negative 2. And we're talking about domain, we're talking about x values here. Goes all the way over until we get to x is 0. What else do we have? Next I see we can go from the hole up here to the hole there. Well, that interval is 0 to 2. And then we have one more. Going from this hole at 2, 0, and tracing up this way. That interval is from 2 to infinity. Keep in mind, all of these are x values, or domain values. So there are 4 open intervals where the function is continuous. One of the new things for today is we're going to talk about what one-sided limits are. So we can find one-sided limits for every function, for every x value. We can find them either from the left or from the right. Here's our notation. If I write the limit as x approaches c, and then I put an exponent that is a negative sign, that is not negative c, that is c to, think of it like a negative exponent, but there's no number attached. Then I write my function. That's equal to the limit from the left-hand side. That means I start on the left side of the x value that I'm approaching, and I move towards the right and say, well, what would the limit be if I was just considering this side of the graph? The other notation is very similar. We find the limit as x approaches c, with a plus sign for the exponent, if you will, of f of x. That's the limit from the right-hand side. And like I said before, for the purpose of this class, we will always be able to find a left or right-hand limit. So now the question is, how do we do that? Once again, we're going to take a look at the graph from the warm-up. We're going to focus on x being negative 2. Now keep in mind, x being negative 2 was this asymptote right here. So we're focusing on that x value. This first piece, the limit as x approaches negative 2 from the left, means start on the left-hand side of negative 2. So let's start at x is negative 4. That's down here. So we're starting here. Now I'm going to read the graph from that point over to the right. So I start on the left-hand side and move over. As I read this graph, where am I headed? I'm headed to positive infinity. So this limit is going to be positive infinity. We are not going to say does not exist for a one-sided limit. We're going to use either positive or negative infinity. Now if I do the limit from the right-hand side, that's what this plus sign after the negative 2 is for. Start on the right-hand side. Let's start at, say, x is negative 1. Now I'm going to start on that side and move towards negative 2, so I read to the left. So I start on the right, read to the left. As I trace, I'm going down to negative infinity. Now, a limit overall means that if you have an answer, you're going to have the same y value from the left and from the right. And clearly, we can see that positive infinity and negative infinity are not the same thing. Therefore, the overall limit does not exist at x is negative 2, which matches the thinking that we have from our previous lessons. Let's take a look at a different x value. So we still have the same graph, but now we're going to look at the limit as x approaches 0 from the left and from the right. So let's start on the left-hand side of 0. Keep in mind, this is not negative 0, this is 0 left-hand side. So here's x is 0. Alright? That's the area that we're going to focus on. We start on the left-hand side of 0, so let's say we start at negative 1. Now I'm going to read towards x being 0, and I go this way. Well, I'm going to get all the way to y is 1. So the limit from the left of 0 is 1. Now let's read it from the right. Let's start at a number to the right of 0. Let's start at x is 1. That's this point right here. And now I'm going to read it towards x is 0. So I read this way, and I'm going towards the hole at the y value 2. Once again, these two values are not the same, meaning the overall limit at 0 does not exist. It's approaching two different values from the left and from the right. But now we're able to identify what is the value from the left, well that's 1, and what is the y value from the right, that's 2. Let's take a look at one more spot. Let's look at the limit as x approaches 2. So that's this section of the graph right here. Here's x is 2. Alright. If I start with 2 from the left, pick a number on the left of 2. So I'm going to start at x is 1. That's this point right here. And I'm going to read towards x equal 2. So I read to the right. I'm going towards the y value 0. I'm never actually going to get there because there's a hole there, but that's okay. Now I'm going to do the limit from the right. That's what the 2 with the plus sign after it means. Start on the right-hand side of 2 and read backwards towards x is 2. So let's start at, say, x is 4. 4 is on the right of 2. And now I read towards x is 2, so I read the graph backwards. Well, there I'm also headed towards that hole, which is 0. Since these two values are equal to each other, that means the overall limit is that value. I'm approaching the same y value from the left and from the right. I hope that this video was clear. We'll go over any questions from this in class on Monday or Tuesday, depending on when I have you.